a very long, straight solenoid. All right, so big idea here. Long and straight solenoid with a cross-sectional area of 2.2 square centimeters is wound with 89.4 turns of wire per centimeter. Starting at t equals 0, the current of the solenoid is increasing according to this formula. A secondary winding of 5 turns encircles the solenoid at its center such that the secondary winding has the same cross-sectional area as a solenoid. What is the magnitude of the EMF? Electromotive force, i.e. voltage, same thing. And the secondary winding at the instant that the current is at 3.2 amps. Okay, so there's a lot of data here. First thing I want to do is I'm going to draw a picture. So we have a solenoid, and this is going to be the head-on view of the solenoid. Here's another view of it from the side. And we have, it's very long and straight, meaning that, that is not long nor straight. All right, so the idea is the straight meaning that under ideal circumstances, all these lines all the magnetic field lines are straight through it, are perfectly horizontal in this drawing. And long, meaning that there's no edge effects. You don't have magnetic fields going like this. So even though I drew them like that, we're just concerned with this inner portion right here, where it's all perfectly horizontal, perfectly straight. And for this, if I draw it over here, we'll draw magnetic field lines going in like so. All right, so we have cross-sectional area, and then we have another secondary winding on the inside. I'm going to draw it like this. Now this is the same area. Even though I drew it inside it, they're really overlapping. So they perfectly overlap each other because they have the same cross-sectional area. And so we have, so for a concept here, I know, very messy drawing, and I am sorry. We have current going through like this. That current going around in a circle is causing a magnetic field to be created within the solenoid. That magnetic field is changing with respect to time because we have a formula up here that says as such. And that change in magnetic field is going to induce an electromotive force, i.e. a voltage, inside in another coil of wire. And a couple of other ideas to kind of keep in mind. I know lots of information. This is a relatively easy question that is not straightforward in any way. So this here is a solenoid, and the red on the inside, this loop is I'm going to say a loop. Secondary winding circles solenoid has a cross-sectional area of, and we're just going to consider the inside to be a loop of wire, 5 loops of wire. Okay, so now we're just going to start doing some math and see where this goes. So whenever we see EMF, we think Faraday's law. So that's supposed to be an epsilon. Epsilon equals negative d flux dt. We can rewrite that as flux is negative derivative with respect to time of b dot a. And these are both vectors. So first thing we see is they don't care about the direction. They're just concerned with the magnitude. So we don't have to worry about the negative sign. Then we know that the magnetic field is straight through, and the area vector for a loop is going to be the normal to the plane of the surface. So basically if you have a circle, this is going to be, pretend that's a circle, but like you're looking at it head on. And I guess maybe not head on, from the side. The area vector for this would be this. Or, to phrase it slightly differently, if you're looking at a loop like this, the area vector then would be pointing straight at us. So basically when they say long straight solenoid, what that's implying here is that we don't have to worry about this dot product right here. That's just going to be 1. So dot product is the measure of how parallel two vectors are. These vectors are going to be perfectly parallel. So we can rewrite this as d dt of magnetic field times area. So there's a lot of simplifications that went on there. You can kind of just assume them, but the problem is written in such a way that they actually are implied and stated. So now, to go a little bit deeper here, to take the derivative of magnetic field times area, we're going to do the product rule. So I'm not going to dwell too much on this. So the product rule of magnetic field times area is going to be magnetic derivative of magnetic field with respect to time times area, plus magnetic field times change in area with respect to time. So the loop and solenoid are not changing sizes, so this goes to 0, which means that this whole term right here also goes to 0. So we're just left with the EMF, electromotive force, voltage, is the change in magnetic field with respect to time times area. So what's going to happen here is this magnetic field is going to be created by the solenoid. So what we need to do is find that solenoid, and that area is then going to come from the windings, the loops on the inside. In those loops on the inside, there's 5 of them, so each of them is basically going to act like a little battery, creating an EMF, a voltage. And since these loops are just connected to each other, we assume in series, there should be 5 of them. Okay, I'll draw the 2 more. Poor use of everyone's time. I know, I'm sorry. So when you have basically 5 batteries in series, or 5 EMFs in series, you just multiply by 5. So we're going to have to remember to do that at the end. All right, so I think we're like 80% done with this problem now. Maybe, at least conceptually. So so what we want to do is, this is the part we're going to focus on. This is our roadmap to success. So we're going to say the magnetic field of a solenoid is mu naught number of loops times current over length. And what they give us is the ratio of N over L. That's supposed to be an L right there. I know it looks kind of like an E. That's okay. So this is going to be mu naught. I'm going to write this as N, which implies that big N over L, which they give us up here as 89.4 turns per centimeter. Ooh, should I know that? Is that important? Maybe. I have to keep that in mind. Yes, times current. So mu naught is 4 pi times 10 to the negative 7, just a constant. And N equals 89.4 loops per centimeter. And what I'm going to do is I'm going to convert that over to meters, just because I don't know if I have to or not. I just want to make sure, just in case. Put everything in SI units. So 89.4 is the same as 8940. I'll call this turns. Loops, turns, same thing. Turns per meter. Okay. And now I, the current, they give us a formula for that. And I'll write I of t because it is a function of t, is 0.167 t squared. And this A and S squared here, those are just amps per second squared. Those are units. They're important, but I'm going to ignore that. 0.167 t squared. 0.167 0.167 t squared. Yep, I'm good with that. And just because I suspect for the future, I'm going to find di dt as well. which is the derivative of current with respect to time, which is just going to be 0.167 times 2 times t. Yep, because we just took the derivative of that. All right, so now we got this going, we got that going. Yes. So that's going to be our magnetic field. And so we know our magnetic field is mu naught n I. Therefore, dB dt, the derivative of magnetic field with respect to time, this is going to be a constant, so we can just pull that out. So we're going to have mu naught n times the derivative of I, which is just I to the first, which becomes di dt, which we just found. So we know the magnetic field, with the derivative of magnetic field with respect to time, is going to be mu naught n 0.167 times 2 times time. And that gives us our dB dt. Then we also need A, which is area, which they just give it to us. So I'm not going to worry about that right now. But one thing we might need to find is this t time. T is question mark, because we don't know what time is. But they gave us some data up here, and they said at 3.2 amps. So I think we can do that. So I'm going to say, this is going to be a little sidebar over here. We're going to have I of t equals 0.167 t squared equals 3.2, because they give us 3.2 amps. Therefore, t squared is 3.2 over 1.67. Therefore, t is going to be the square root of that, but I'm going to write out the square root just because I don't like writing square roots. It's a personal animosity of mine. Second square root of 3.2 over 1.67. So 3.2 over 1.67. This seems reasonable. And that gives us an answer of about 1.38. 1.38 seconds. So this gives us our t now. So we got the t up there. And so it looks like we have everything we need for dB dt. We're going to go back to our roadmap up here, which was dB dt times area. And we're going to write this out as, let's see here. We got mu naught, which is 4 pi times 10 to the negative 7. We have number of turns per unit length, which is 8940. That's supposed to be an 8. And then we're going to have 0.167. And there's going to be a 2. And there's going to be a t. There's probably some canceling here that I could have done to make life easier. That's okay. And this is just the dB dt, the change in magnetic field with respect to time. So now we're going to multiply this by the area. They give us the area, which is something something centimeters squared. I thought they did. 2.12 centimeters squared, which is 2.12 centimeters squared, which I'm going to write as centimeters times centimeters, just because that way it's easier for me to convert it. So we have 100 centimeters per 1 meter times 100 centimeters per 1 meter. And I probably could have done everything in the same unit somehow. I don't trust my math that much, so I like to convert everything to SI units just to even the playing field. And then that's not the real area, because that's the area of one loop. It says that we have a total of 5 loops, so we're just going to have to multiply that by 5. And that's what I talked about with the idea of having batteries in series. And so this is, I think, the whole concept here. So let's put in these numbers. So we're going to have many numbers. 4 times 3.1415. I know there's a pi button, but I don't care. Times 10 to the negative 7 times 8940 times 0.167 times 2 times 1.38, which I know that could be more exact, I don't care. 2.12 divided by quantity 100 times 100 times 5. Maybe. Let me check, see what this is. 5.46 times 10 to the negative 6 volts. Let me see. Is that what I got? 5.49. Just a second. I think that's, right here. Fail. Not 1.67. That's where I think I got tripped up. So going back to this, second square root of 3.2 divided by 0.167, not 1.67. That gives us 4.377. 4.377. And so now we go back to this and we plug in 4.377 here. We get a different answer, and we get a value of 1.74 times 10 to the negative 5th. This was a negative, even up there when I got the answer wrong. Volts. So key idea here, my failing, was decimal. Wrote the number wrong. Should be 0.167 instead of 1.67. So when we plug that answer in, plug in that correct time up there, plug into our formula, then we should get 1.74 times 10 to the negative 5th volts. That's how you approach this problem. So let's recap real quick because there's a lot of craziness that went on. We have a solenoid around a coil of wire, a loop of wire, and that solenoid has a current running through it. That current creates a magnetic field. That magnetic field inside that solenoid, which is long, straight, uniform, horizontal, concentric with our loop, is going to be changing with respect to time. That change in magnetic field is going to induce a voltage in our loop, and it's going to do so according to Faraday's law. We went through Faraday's law, which is really, which simplifies out to the dot product between the magnetic field and area, taking the derivative with respect to time. We went through the simplifications, and we got that the voltage is going to be change in magnetic field with respect to time times area. And that's the area of the inner loop, which is concentric and the same size as the outer loop, as they said in the problem. So then we did a bunch of math. We found a value for time, given what they gave us for initial conditions. And we ran with the idea of EMF in this case is going to be the change in magnetic field with respect to time times area, where the magnetic field is related to the current through the solenoid. And we got this giant equation here. We multiplied it out, and when we multiplied it out correctly, we got an answer of 1.74 times 10 to the negative 5th volts. So the problem itself isn't too complicated, but there's a lot of nuance in the question that is easy to gloss over and is worth understanding. So hope that helped. See you next time.